All right, good evening, everyone. So today, so here's the arrangement for today. For the first 2 hours, I will give lecture about so we'll finish up edge detection, and then we'll introduce a little bit about local environment features. Then the TA will walk you through lab 1, okay? So last time we stopped at the third step of Canny edge detector. Do you still remember what it is? So for Canny edge detector, initially we can apply a separate Gaussian filter to suppress noise initially. And then we apply the Sobel. The Gaussian kernel depends on the kernel size. The Gaussian kernel, it has different size. And we have seen some examples of Gaussian kernel. So this is a 3x3 Gaussian kernel, and this is a 5x5. So here, theta corresponds to the size, the kernel size. So if you apply larger kernel on the image, the resulting effect is a larger kernel, which corresponds to larger filters. Example, 5x5 filters. Okay. And if you apply larger kernel Gaussian filter over the image, and you will see, this is what you will get. This is the input. You will see compared to the filtering results by small filter, smaller kernel, smaller size of Gaussian kernel, larger Gaussian kernel will detect larger scale edges, while small Gaussian kernel will preserve fine features. So remember, when we say Gaussian kernel, we mean the Gaussian derivative of Gaussian kernel in the Canny edge detector. So the typical workflow in Canny edge detector is initially we may, apply a separate Gaussian smoothing filter to suppress noise in the image. And then we apply the Sobel detector. We apply Sobel detector. Okay, so the first step, you apply a separate smoothing filter. This one is optional. If you want to suppress noise, you can apply a separate Gaussian smoothing filter to remove or reduce noise in the image. Okay, and then you apply Sobel detector. What is Sobel? Sobel operator. Sobel operator apply the derivative of Gaussian filter. So again, here we have another Gaussian filter, but we take the derivative of Gaussian filter. Okay, so in the Sobel operator, it already suppress noise using Gaussian filter. Okay, because as we introduced last week, we want to smooth first. We want to take the derivative, this derivative of Gaussian, because the natural image often comes with noise. That's why we want to apply derivative of Gaussian. derivative of Gaussian filter. We want to convolve the input image with the derivative of Gaussian filter. So Gaussian filter itself can smooth the image, while the derivative of Gaussian filter can smooth the image while simultaneously detecting edges. Okay. So in Canny edge detector, the first step is optional. You can apply an additional Gaussian filter to suppress the noise. And then you compute the gradient magnitude and direction using Sobel operator, where the Sobel operator is actually the derivatives of Gaussian filter. Now, here comes the third step. The third step is called thinning. So the purpose of this step is to assure minimal response in the edge map. So after Sobel detector, what we get is typically this edge map. Not this edge map. This is this is the gradient magnitude map. This is the gradient magnitude map. And you can see there are multiple response along the edge. Okay, and which is not ideal. So we want to suppress those responses. We want to assure minimal response. That's why we need to do non-Masterman suppression. And non-Masterman suppression is to remove redundant edge pixels by suppressing non-maximal gradient. So this can be done by along the rounded gradient direction or along the real gradient direction. So as we explained last time, if we can do the suppression along the rounded gradient direction because an image is discrete and it has at most there are only 8 angle direction over the image. Okay, so this is the real gradient direction. So we can round this gradient direction by looking for the angle direction that is closest to the real gradient direction, which is this one. So this is the red one indicates the rounded gradient direction because this is the angular. This is the angle direction closest to the real gradient direction. Okay, so we can perform non-Masterman suppression along this direction by comparing the gradient value of this pixel and this pixel and this pixel. And we only keep the largest one. So that's how we do non-Masterman suppression along the rounded gradient direction. We can also do it along the real gradient direction indicated by the green one. Okay, along the real gradient direction. But there are no pixels. The neighboring pixel, the 2 neighboring pixels, they're not real pixels. They do not exist within the image. So we need to calculate their gradients by interpolation. That is, we can compute the gradient for this fake pixel by doing interpolation, by using the gradient value of this pixel and this pixel. Okay, so if we want to do non-maximum suppression along the green direction, we need to know the gradient value of this point and this point, which are not real pixels. They do not exist. These pixels do not exist. Okay, then how can we compute their gradients? We use interpolation. So the gradient of this pixel can be obtained by for example, the average or combination of its neighboring pixels. Okay, so once we have the gradient of the two pixels, we can do non-maximum suppression by comparing their gradient magnitudes, the gradient magnitudes of the three pixels. Okay, so that's non-maximum suppression. And you can see after non-maximum suppression, we have for each edge, there's only one pixel reserved along. I mean, the edges are thinned. Okay, after non-maximum suppression, then there's only the width of the edge is only 1 pixel. So the effect after non-maximum suppression is much more desirable than before. Okay, and finally, this is still not the edge map we want because we haven't do thresholding yet. Okay, so this is the gradient magnitude map after non-maximum suppression. Okay, this map is the gradient magnitude map, whereas this map is the gradient magnitude map after thinning, after suppression, non-maximum suppression. Okay, so here comes the final step. We want to threshold the image and obtain the edge map, the final edge map. Okay, so the last step is to is called threshold hysteresis thresholding. As we explained in last week, it's difficult to choose an appropriate threshold. If you set the threshold too high, you don't get a full edge. You don't get there are many breakups. You only get discontinuous edges. But if you set the threshold too low, you may retain too many details. Okay, so it's difficult to set an appropriate threshold. So here the solution is to define two thresholds. Okay, so we set a high threshold. We set a high threshold to start with strong edges. Okay, we set a high threshold, and if the pixels, if the gradient magnitude of the pixels are greater than the high threshold, then these pixels represent strong edge pixels, and they should be reserved. And conversely, if their gradient magnitude are lower than the low threshold, then we say these pixels are definitely not edge pixels. Then what about those in between low and high? Then it depends. It depends on whether these weak pixels are connected to the strong pixels, strong edge pixels. And if they do, then they're also considered as edge pixel. Okay, so hysteresis thresholding is an approach to avoid breakups in edges when you have a very high threshold, you have many breakups in edges. Okay, so to adjust this, we set another threshold, the low threshold. Okay, so for those between low and high, we consider for those threshold between low and high, we consider whether this pixel is connected to a strong edge pixel, either directly or so if this weak pixel, if those weak pixel between low and high, if they are connected directly to a strong edge pixel, they are also considered edge pixel. If they are not directly connected to the strong edge pixel, but they are connected to the strong edge pixel via weak edge pixels, then they are also considered edge pixels. Okay, so first of all, let's take a look at an example. For those pixels whose gradient magnitude is below the low threshold, so this one, D, the pixels of D, they're not edges, not edge pixel. Okay, the pixel of A are considered strong edge pixel, and so is the pixel of B. So this for these pixels, because their gradient magnitude is higher than the high threshold, so these are considered strong edge pixel. Okay, so to begin with, these strong edge pixels are connected. They are connected with this weak edge pixels. Okay, that because they are connected with those weak edge pixels. So this pixel is connected directly. It's connected directly to the strong edge pixel. So this pixel is also considered as edge pixel. And the pixel next to it, this one, is also considered an edge pixel because it's indirectly connected to B. It's connected to B, to the strong pixels here via another weak pixel. Okay, so it's like this it's like this connectedness is transferable. So if this part is strong edge pixel, and these pixels, these weak pixels are connected with the strong edge pixels, they are all considered. They're all preserved. They're all considered edge pixel. Okay. However, pixels of edge E, pixels of this, they're not considered as edge pixels because they are not connected with strong edge pixels. Clear? So this is the underlying idea for hysteresis thresholding. So hysteresis is a physics term. So it means when we consider the current situation, when we consider the current situation, we also need to consider the past conditions. So it's like these pixels are connected, and if we want to know whether the current pixel, this one is an edge pixel or not, we need to take a look at its neighboring pixels, whether they are connected with strong edge pixels. Okay, so this is the idea of hysteresis thresholding. Another example is this. So these pixels, they are strong edge pixels because they will look at the width of these pixels. So they are strong edge pixels because their gradient magnitude is higher than the higher threshold. And these are also strong edge pixels because their gradient magnitude are also higher than the high threshold. Well, interestingly, for these pixels between these pixels between the two strong edges. They are weak, but they are connected. They're connected to strong edge pixels. So they are also considered edge pixels, and they should be preserved on the edge map. Okay, so this is the idea of hysteresis thresholding, and you can see from the results that hysteresis thresholding achieve a better trade-off between applying high threshold and applying low threshold. Like we said before, if we use low threshold, there are many weak edges. And if we apply high threshold, there are many breakups in the edges. So hysteresis thresholding use high threshold to preserve strong edges. And they use those strong edges to connect with weak pixels, weak edges. Okay, and they apply low threshold to filter out weak edges. And only the weak edges that are connected to strong edges are preserved, are kept. Okay, so that's why we say hysteresis thresholding achieve a better trade-off between high threshold holding and low thresholding. So finally, with these steps, non-maximum suppression and hysteresis thresholding, this is what we get. A pretty good edge map. We call this edge map. And the edge map is a binary image. Okay, so the pixel value could be 255 and 0. So the edge pixels correspond to pixels with non-zero values. Okay, this is also the final output, the edge map. Okay, so this is the summarization. So these two steps are considered Solvay, okay? And before applying the Solvay operator, there's an optional step, optional step to smooth the image. Okay, and then we thin the third step is to thin multi-pixel wide ridges down to single pixel width, thinning the edges. And then the last step is to thresholding, using the high threshold to start edge curves, using high threshold to keep strong edges to start edge curves, and the low threshold to continue them. Okay, so this is a video about candy edge detector, which we'll skip here, and you can watch it offline. And we have already seen this map, 45 years of boundary detection. So the performance of edge detector is indicated by this green, by this blue curve, which is pretty good. Okay, so anyway, this one. So candy edge detector is a classical edge detector, and you will, in your lab 1 assignment, you will do some programming exercise by implementing the candy edge detector. And also in your lab 1, there's a bonus point regarding Hopf transform. So in the following, I'm going to briefly introduce Hopf transform. Okay, so Hopf transform is introduced by Hopf. Well, a few decades ago. So the goal is to find the location of lines in images. Well, let's take a look at this. This is the input image. This is the input image, and the middle one. The middle one is what? Is the gradient magnitudes. Okay, gradient magnitudes. We have performed, for example, Sobel detector, and we have obtained a gradient magnitude. This is the gradient magnitude map. Okay, and this, you can see there are many breakups in the images. This is the edge map. This is the edge map after we apply thresholding. Okay, the last one is the result of thresholding, and the last one is the edge map. Okay. So what can we observe for the edge map? There are many straight lines. There are many straight lines in the input image, but on the edge map, we only have pixels, a set of pixels that may partially describe the boundary of the objects. Okay, so for example, there should be a straight line here, and there should be another straight line here. Okay, instead, on the edge map, these straight lines only described, they are only described by some pixels, which means we don't get the full, we don't get the full lines. We don't get the full lines. So half transform is designed to obtain results like this. So as you can see, there are 20 lines. The most voted, the most significant you can consider are 20 most significant lines in this image. So half transform is to identify the location of the most significant straight lines within the image. Okay, so on the edge map, this is the result of edge map. How can we identify the top, for example, the top 10 or the top 20 most significant lines within the edge map or from the image? So this is what half transform was proposed for. To identify the goal is to find the location of lines in images. To identify the most significant lines, we want to fully describe the lines. We want to know the equation of those lines. Okay, if we know the equation of those lines, then we can identify all of them. You know what I mean? For example, for this line, okay, if we know on the edge map, this line is described by a set of pixels. Okay, it's described by a set of pixels, but we do not know the equation of this line. We do not know the equation of this line. Okay, then how can we identify? If we know the equation of this line, we can identify its location, because the equation of this line gives a full description of this line. Another example is this one. Okay, this line. Yeah, on the edge map, there are only some pixels. we know there are some pixels sitting on the same line, but we do not know the location, the equation, or the location of this line. Okay, so Hopf transform is designed to identify the top most significant lines within the image. And as you can see, those lines they are shown clearly over the image because we know exactly what their equation is. We know the parameterization of this line. Okay, and also this line. For each line, we know their full equation. We know the parameters of this line. That's why we can draw the full line over the image. So do you have any idea how we can do that? How we can achieve that Hopf transform? Now let's look at this edge map. How can we identify the most significant lines from this edge map? So which lines appear to be the most significant? I would say this line. Which line appears to be the most significant? Perhaps this line or this line. So if we know how many pixels belong to this line. Okay, if we can identify the set of pixels that belong to the same line, then maybe we can determine the most significant lines by voting. Okay, so for example, if we know they are 100 pixels, then 100 pixels belong to 100 edge pixels. You know, edge pixels are those pixels after thresholding, the pixels left on the image after thresholding. So if there are 100 edge pixels belong to this line, and for example, there are 80 pixels belong to this line, or there are 120 pixels belong to this line. Okay, if we can identify for each line, the number, how many pixels belong to each line, then we can set a threshold. Okay, and we can select those lines which are represented by these pixels, and this requires us, you know, from the edge map, we need to be able to identify which pixels belong to the same line. Okay, so we need to be able to identify these pixels belong to this line, and also these pixels belong to this line, and these pixels belong to this line. Okay, we need to be identifying which pixels belong to a specific line. And meanwhile, we need to figure out the equation. We need to figure out the equation of this line, the parameters, the slope and the intercept, of this line. Okay. Okay. So how do we do that? You notice that if all these points belong to the same line, then these points, they share the same slope. They share the same slope and the intercept. Okay, so in Hopf transform, we want to find set of pixels that make up the straight line. The set of pixels make up straight line. This set of pixels make up one straight line. Okay, this set of pixels make up one straight line. And if we can identify them, we can also identify the equation of the line, including the slope and the intercept. Okay, so in Hopf transform, Hopf transform is based on an observation that Hopf transform is to consider another space. Let's call it dual space. We call the original space, this space, the edge pixel space, we call this XY space. So for each point, for each edge pixel xi, yi, if for those edge pixels, if they belong to the same line, they share the same slope and the intercept. Because xi, yi, this is a point. So we have x1, y1, x2, y2, and xn, yn. Suppose the n points, they all belong to the same line. They all belong to this line. Okay? Then these points will satisfy this equation. Will satisfy the equation because they all sit on the same line. They will satisfy this equation, all these xy points. Okay? They will share this equation. Common to them is they share the same slope and the intercept, A and B. Okay, clear? Well, if we consider the dual space, in the dual space, the parameters are A and B, while the variables become the variables are A and B, and the parameters becomes SI, YI. So this is the original SY space, while this is the AB space. We call the AB space dual space. Okay, so in the original edge map, which is the XY space, we have 2 points, for example, 2 edge pixels belong to the same line. Then each edge pixel will give a straight line in the AB space. Okay, so this is a little bit hard to comprehend, because what we want to find, the goal here is to find set of pixels. The goal here is to find the set of pixels that belong to the same line. And our approach is to map each pixel in the XY space to a straight line in the AB space. Okay, so this pixel whose coordinate is 1, 2, this pixel is mapped to a straight line. This line is mapped to a straight line in the AB space. This pixel, 1, 2. So initially, its coordinate in the AB in the XY space is 1, 2. But in the AV space, this is 1, this is 2. So 1 and 2 becomes the slope and the intercept in the AV space, because in the AV space, A and B are variables. Okay, so in this case, 1, 2 here, 1 and 2. This point correspond to a line in the AB space, where the line, for this line, its slope is 1 and the intercept is 2. Okay, so a point gives a line in the AB space. And similarly, this point, 0 and 1, gives another line. It gives this line in the AB space. Where for this line, the slope is 0. The slope is 0. The slope is 0. The intercept is 1. Okay? So their intersection in the AB space, the intersection of the two lines is 1 and 1. And their intersection correspond, 1, 1 here, correspond to the slope and the intercept of the of this line in the XY space. Okay, so I hope you can figure out this. So initially, what we have is points. Initially, what we have is the points in the XY space. Xi, Yi are the coordinates of those points. Okay. For those Xi, Yi, as we say, X1, Y1, Xn, Yn, if they belong to the same straight line, then they will share the same A and B. Okay? And if we consider, if we write this equation, Yi equal to A xi plus b. So this is the equation in the xy space. Okay? And this equation can be written in an equivalent way. So we just move this to the other side. So we can write this equation as b equal to this. Okay? They're equivalent. But now let's consider the dual space. In the dual space, the variables are A and B, while Xi, Yi are the parameters. Okay? So therefore, if for Xi, Yi in the XY space, it corresponds to a straight line in the AB space, because Xi, Yi, they are considered as parameters in the AB space. Okay, so here we have this 1, 2. This is in the XY space, and 0, 1. We have 2 points, 1, 2, and 0, 1 in the XY space. So this point 1, 2, you will give a straight line. You will give a straight line in the AB space, because 1, 2, you will determine the slope and the intercept of the straight line in the AB space. And similarly, this point 0, 1, you will give another line in the AB space with slope 0, and the intercept 1. Okay, the two lines will intersect. The two lines will intersect at a single point, 1, 1. And this 1, 1 is the parameters of the straight line in the xy space. So it's like they have this dual relationship. They have this dual relationship that points in the xy space correspond to parameters of straight lines in the AB space. Okay, and the intersection of the straight lines in the AB space correspond to the parameters of the line in the xy space. So half transform will this is just not straightforward to comprehend. Okay, so what we do is for example, this is the AB space. In AB space, we have 1, 2, 3, 5, 4, 3, 4, 5. We have 5 straight lines intersect at 1, 1. Okay, in the 1, 1. So this is 1, 1. This line. This line. Okay, so there are 5 points. There are 5 points along this line. There are 5 points along this line in the xy space, and each of them correspond to a straight line. Each of them correspond to a straight line in the AB space, and they all intersect. Their intersection 1, 1 correspond to the slope, the parameters of this line, the slope and the intercept of this line. So half transform just utilize these dual relationships to identify the set of points that sit on the same line. Well, the algorithm for half transform is to quantize. First, let's quantize the parameter space A and B. Because in half transform, we want to identify this. This is the equation. Okay, we have 5 points from SY space, and they correspond to the straight lines in the AV space. Their intersection 1, 1 are the parameters of this line. And which are the location, which are the equation of this line that we want to identify. Okay, so their intersection in the AB space 1, 1 are the parameter of this line, the parameters of this line that we want to identify. Okay, so the algorithm of half transform is to quantize. Let's first quantize the AB space by dividing them into cells. Okay, so we just divide. We just divide AB space into cells. You can see there are many cells. Okay, these are the cells. There are many cells. There are many cells. Okay, and we count the number of times a line intersect a given cell. For every pair, for every 2 points, for every 2 edge pixels, we find their intersection A and B in the AB space. Okay, for example, for the 2 edge pixels, because each edge pixel corresponds to one line in the AB space. For any 2 edge pixels, we find their intersection. We found their intersection in the AB space, and we increase the value of this cell And so 1 here. So we may want to increase the value of this cell because they intersect at this cell. Okay. So we do this for every pair of points. For every pair of edge pixels, every pair of edge pixels correspond to two lines in the AB space. So we calculate their intersection points, and we increase the number of counts of the corresponding intersection cells. Okay, so we do this for every pair of points. And finally, cells receive more than a certain number of counts are assumed to correspond to a significant line in the SY space. Okay, so it's not straightforward. I hope you can figure out the relationship between the original XY space and the AB space. So basically, for each point in the XY space, each point in the XY space will give a straight line in the AB space. The point 1, 2 correspond to the parameter, the slope and intercept 1, 2 of this straight line in the AB space. Okay, this point corresponds to another line in the AB space. So for every pair of edge pixels, we compute their intersections, and we increase the corresponding cell in the AB space. So we do this for every pair of edge pixels from the edge map. Okay, so finally we will obtain this AB cell, and for some cell, the count, for example, for this cell, the count should be could be 30, and for this one, the count is 20, and for this one, the count could be 15. Then this AB cell, the coordinate of this AB cell correspond to the parameters. So this indicates there's a straight line with these parameters, with the corresponding AB value. It corresponds to the parameters of the line in the original XY space. And similarly, the AB value here corresponds to another straight line in the XY space. So it's this one. So we just identify the cell with the most counts. The cell with the most counts. So the larger the counts, indicates more significant lines. Larger counts indicates there are many points. There are many points on the same line, belong to the same line. So this is the idea of hot transform. Okay, let's take a short break. right? So let me try to explain half transform again. So the first step is let's quantize the parameter space. Let's quantize the dual space, AV space. Okay, so let's quantize the AV space by dividing the AV space into cells. As you can see, there are many cells here. And for each cell, it corresponds to an AV value. For example, this cell, the AV value for this cell could be it could be 1.7 for this cell, 1.7, and sorry, the AV value for this cell may correspond to where the A value is close to 0. The A value is close to 0. For this cell, the A value may be close to 0 and the B value could be 1.8, for example, for this cell. Okay? So the first step, we quantize the space by dividing into cells. And for each cell, it corresponds to a pair of AB value. Like I said, for this cell, the AB value may be A being 0, B being 1.8. But for this cell, the AB value may be A being 0, 1.6. And similarly, for this cell, A is also 0, but the B value could be 0.8. Okay, so for each cell, it corresponds to there's an associated AB value. Then we count for each pair of points, for each pair of edge pixels within the edge map. For each pair of edge pixels within the edge map. Because each edge pixel gives a straight line in the AB space, then a pair of edge pixels will give 2 lines. It will give 2 lines in the AB space. So we can find their intersection. Their intersection in the, for example, the 2 edge pixels will give 2 lines in the AB space and they intersect at this point. And let's say these points belong to this cell. Belong to this cell, the yellow one. Okay, the intersection belong to this cell. And then we increase the value of this cell. Okay, so we identify their intersection points. And if this intersection point belong to a certain cell, belong to this cell, then we increase the count, increase the value of this cell. Okay, so we do this for every pair of points within the edge map. And finally, we can get some count. We can get some we can get some accumulated cell like this. Okay, and you can see this cell, it has count 27, and this cell, it has count 30, which means they are 30. The straight lines intersect 30 times. The straight line intersects 30 times at this location. And similarly, the straight line intersect 28 times at this location. Then for this cell, the straight lines intersect like 10 times. And for this one, the straight line intersect 2 times at this cell. And for this one, the straight line only intersect 1 time at this cell. Okay? Okay, now we have the cell count. The cell receiving more than a certain number of counts Now we have the cell counts. We would like to identify the cells that receive the most counts. Let's say if we want to identify the top three cells, the top three cells are 27, 30, and 28. So the three cells receive the most counts, which means there are many straight lines intersect at this cell, and this cell. Okay. Then their cell value, I mean their corresponding AB value, for example, for this 27, for this cell, the A value is 1 for this one, okay? The AB value for this cell is 1 here, okay? The A value is 1. And the B value should be 1.8, for example. Okay? Then 1.8 correspond to a straight line. It corresponds to the parameter of 1.8 correspond to this line in the original space. Okay, so 27, this cell correspond to a line with slope 1 and intercept 1.8 in the AB space, in the XY space. And similarly, 30, this cell, let's look at its AB value. Well, A could be 1.6, and its B value could be also 1.6. Okay, so this cell correspond to another line, another line in the XY space. And similarly, 28, this cell, for this cell, its A value is 2, and its B value is 1, 2, 1. So this cell correspond to another straight line. Okay, another straight line in the XY space, for example. Okay, so by identifying the cell with the most counts, we can immediately know this cell represents the most significant line in the XY space. The cell, for each cell, we can identify the associated AB value. The AB value correspond to the parameter of the line in the XY, the original image space. Okay, so that's how we identify the line equations. We identify the cell that receive the most counts. And for those cells, we identify their corresponding AB coordinates. The AB coordinates correspond to the parameters of the line in the XY space. Clear? So that's how we do half transform. So I hope you can figure out this, because I don't know how to explain this more clearly. So the top 20 voted line, each line correspond to a cell in the AB space, and the parameter of the line, the parameter are given by A and B, correspond to the coordinate of that cell in the AB space. Okay, this expression, this representation, this may not be the ideal way to represent a straight line, although this is the most common way to represent a straight line, the slope and the intercept. Okay, but what if we want to represent vertical line? If we want to represent vertical line or nearly vertical line. A will be a very large number, right? A for vertical line, A goes to infinity because its slope goes to infinity. So this representation is not friendly for representing vertical or nearly vertical line because A will be very large. A will be very large. So think about this. If we want to represent a vertical line, then we need to consider very large A. And we need to quantize the AB space. It will be difficult to quantize the AB space if we need to consider very large A. So therefore, we resort to polar representation. Polar representation. So we represent a line, so this line, by using the theta. Theta means the normal. This is the normal vector. This is our line. This is our line, okay? And we represent this yellow line using theta. Theta. Using it's the normal vector and the angle between x. So we represent this line using theta and rho. Well, theta is the angle between the normal vector. This is the normal vector and the x-axis. Okay. This angle is theta, and rho is the distance from the origin to this line. The distance from the origin to this line. Okay. So you can figure out the polar coordinate representation of this line. Why this line can be represented by cosine theta, x cosine theta plus y sine theta equal to rho. Right? You can figure out why this straight line can be represented in this way. Okay? So now the straight line is represented using theta and rho. So now we can represent vertical line. Vertical line correspond to, theta being 0. While horizontal line correspond to theta being 90. Okay, you can imagine we rotate this line to the vertical line, then theta will get smaller. We rotate this, okay, counterclockwise, and this line will become vertical, and this theta will become smaller and goes to 0. Okay, so when theta goes to 0, it represents vertical line. When theta goes to 90, so if we rotate this line clockwise, then theta will become 90 when the lines becomes a vertical horizontal line. Okay, so using polar expression, we can represent vertical line conveniently when theta is 0 and horizontal line when theta is 90. Okay, so this is just another expression of straight lines. It also has 2 parameters, theta and rho. And similarly, a point on the line in the xy in the rho theta space in the original space, xi yi. A point in the original space correspond to, this is xj yj. Xj yj correspond to now a curve. It corresponds to a curve, this curve, in the rho theta space. Okay, this point, xj yj, correspond to this curve in the xj, yj, in the rho theta space. And the xi, yi, this point correspond to another curve in the rho theta space. Their intersection, the rho theta intersection correspond to the parameter of this line in the xy space, rho theta. Okay, so everything is similar, except we represent the line using polar representation, polar coordinate representation. Okay, but the insides are similar. Okay, well, the algorithm is simplified. I won't go into details, but you can figure out. In this algorithm, the algorithm is more efficient because we do not consider every pair of pixels. We do not loop through every pair of pixels within the edge map from the original space. But we quantize rho theta. And for each edge pixel, we just calculate a few theta. Because each edge pixel, it gives a curve. In the rho theta space. And we quantize rho theta space. So this curve, the yellow curve, you only intersect. The yellow curve only intersect a few cells. So we only need to consider, a few thetas. We only need to calculate. We only need to calculate a few thetas. For this theta, we need to we calculate the rho. Okay, so we only need to calculate the quantized theta. The quantized theta for each theta, because we quantize the rho theta space. So within the quantized rho theta space, we only need to consider, for example, theta 1, theta 2, theta 3. Okay, for each theta, we calculate rho. For each theta, we calculate, this is the rho. For this theta, we calculate this rho. Okay, and then we increase the corresponding rho theta cell. So that's how we made the computation more efficient. Instead of calculating the intersection of any two curves, we calculate for each curve. For each curve, we only calculate a few theta rho values. We only calculate theta 1, theta 2, for example. Okay, for this, we only calculate a few points for each curve. We only calculate a few points for each theta. Okay, and then we increase the accumulator at the corresponding rho theta. So this algorithm is more efficient than this one, than the AB, the original representation, the ordinary representation. Okay, and as you can see in the image space, if there's a line in the image space, then each point will give a curve in the y space, well, you cannot see the curve here because they are two you cannot see the curve here because they are because the high contrast, you know, the curve, each point corresponding to a curve in the rho theta space, and you can see they intersect at one point. All these points, each point will give a curve in the rho theta space, and all these curves will intersect at a single point. So this point corresponds to the parameter of this line, the parameter of this line. Okay. And likewise, for this example, these points they do not sit exactly on the same line, but they are very close. They're very close to this line. So therefore, in the rho theta space, they intersect at roughly at a single point. Okay, roughly a single point. So this point, this cell value, this rho theta value, correspond to the parameter of this line. Well, for this case, because these points they just randomly distributed and they do not belong to the same line, and in the rho theta space, you can see they do not intersect at they do not intersect at one point, or so there's no clear pattern with regard to the intersections. Okay, so anyway, the half transform is just the half transform is not easy to comprehend, but it's an elegant way. It's quite elegant, conceptually simple, but it's an elegant approach to handle missing and occlude data very well. And you can see from the output, the half transform, because it can identify the equation of the lines. So we can draw the whole lines without the whole lines because we know the full equation of these lines. So you handle the occlude data. You handle missing and occlude data very gracefully. So even though part of line are blocked, are missing, we can still reconstruct the line because we know the full equation of the line. Okay. And half transform can be applied to identify lines, but not only lines. It can also be applied to identify circles. For example, circles, ellipses. As long as these shapes can be parameterized. Okay, as long as these shapes can be parameterized. So it can be identified to arbitrary shape that can be parameterized. But it cannot simultaneously identify, for example, line and circles. Okay, it cannot detect both shapes simultaneously. It can only look for one type of object. So you can we can either apply it to identify line or circles, but we cannot apply one half transform to identify both line and circles. Okay, and the half transform, because it gives the full equation of the lines, it cannot determine the length or position of the line segment. A portion of the line cannot detect the segment, the segment or the length of the line, because it just gives the full equation of the straight line. Okay, so this is what I want to say about half transform. while it's an elegant algorithm, it's not very easy to understand. That's why the exercise about half transform leave as the bonus in your lab 1 assignment. Okay, so if you feel comfortable, if you want to do it, just do it. Okay. So we have 20 minutes left. Let's move to study chapter 5. Local invariant features. So in this chapter, we want to introduce the SIFT algorithm. The SIFT algorithm is to identify interesting, well, there are two adjectives, local, interesting local features, and invariant features. Invariant means what? Invariant means the features may be robust, invariant to, for example, rotation and the scaling. Okay? As you can see, there are many sunflowers. There are sunflowers, and each sunflowers, this one may represent an interesting feature. Okay? And these sunflowers, they have different scale. They have different scale and orientation. Okay, so we want to, for example, we call this feature blob, and we want to be able to identify these features, the blob features, regardless of its scale. So the feature could be, scale invariant. And actually, the SIFT algorithm or the SIFT feature stands for scale invariant feature transform. Okay, scale invariant feature transform. Now, back to the introduction of local invariant features. So given multiple images, so previously we only deal with single image, whether we do edge detection or color transformation. We only deal with smoothing, edge detection. Okay, we only deal with one image. Now we are dealing with multiple images, and we want to be able to, for example, to do matching. We want to be able to match this object with this object because they are the same object. Okay, we want to establish the correspondence between this image or this object with this object. We want to do matching, and we want to connect different view, multiple images to form a panorama like this. Okay, we want to be able to put multiple images together to provide an image with a bigger view or a more complete view. It's called panorama stitching. We want to combine two images together. And how can we do that? To perform this task, we need to extract some key points. Or from each images, and we want to match those key point features. Okay, for example, we want to match this point with this point. Of course, each point will be represented as a feature vector, and same points. So we want same points they have similar feature vectors, so we can match them. Okay, and that's how we do the stitching, like this. So we stitch two images together because we can establish their correspondence, the correspondence between their key points or feature points. Okay. Here's another example. We have NASA Mars rover images. So these images are taken from Mars. The two images are taken from Mars. Can you identify, the same areas from the two different images? The two images contain the same area or region, same location. The corresponding points are actually here and here. Okay. So the two regions, these two regions are the same regions on Mars. And this correspondence, these feature points are detected by SIFT with the SIFT feature. SIFT feature matches. Okay, so the correspondence are actually not easy to be identified by by our naked eyes. Okay, but actually we can see the correspondence on the two images. Okay, so these feature points are identified by SIFT detector, and you can see those little squares. Those little squares, they have different color, they have different size, indicating the scale of the feature points. So larger square represent the larger scale. These feature points come with different scale, represented by the size of the square. Okay, here's another application of real-time image stitching. So you can see the signals are from two individual sources, and these two video signals, the video sources are combined together in real time. Another example for real-time video stitching. Okay, so you can see the man appear in different video frames. You know, the camera, the surveillance camera, the footage from the surveillance camera that are stitched together, together to give this view. Okay. So so this is actually your lab 2 assignment. You know, today we will have lab 1. We'll have the TA introduce lab 1, but in 2 weeks. In 2 weeks, October 23rd, we're gonna do lab 2. Okay, in 2 weeks, lab 2. So, originally we should do lab 1 on October 2nd, but because my illness, it was postponed for 1 week. Therefore, lab 2 is scheduled on October 23rd. Okay. We still have 5 minutes. Let's watch this introduction of SIFT detector.
We know how to find edges and corners in images. And then we also know how to take these edges and corners and then compute the boundaries of objects in images, which is very useful in computer vision. Now let's talk about the problem of object recognition, in particular recognizing objects with fairly complex appearances. In this case, you want to be able to detect and match features that are fairly descriptive and unique. And that's what the SIFT feature detector does for us. But let's start with a little quiz. So here is an image shown to you, and the question is, what technique would you use to recognize the objects in this image? But this is a fairly simple one. We know from our lecture on binary image processing that we can probably apply a threshold to this image and get a nice clean binary image, and then compute the geometric properties of these objects in the binary image to recognize them, to find their orientation and their position as well. So that's an easy one. Now let's take a look at this image right here. So here again, maybe a slightly more complex image, but once again, you can imagine that you can apply some kind of a thresholding scheme to extract the letters and numbers on these license plates, and then use a simple recognition technique to find them, to recognize them, and read out these license plates. Not too hard. Now let's make things a little bit more interesting and consider this case. So here is what we call a 2D object. It's a planar object, but with a fairly complex appearance. And we want to find this object in this image right here. So what technique would you use? Well, your first instinct...
So how do we find this object? How do we find this object from here?
Maybe to use something like template matching. We know how to do that using normalized correlation. But the problem is...
So this, if we consider this as template, we can do template matching, but as you can see, part of this object is occluded by other objects, and also this one. And also there are the orientation of this object, these two objects, and their scales are different.
Is that the object doesn't show up exactly in its original form in the image, it's actually rotated in the image and is also magnified differently. In other words, it has a different scale in the image. And so, in order to deal with rotation and scale, you might have to then create lots of templates of this object under different rotations and scales and apply each of one of those to the image, which would be computationally just impractical. But actually, the harder problem here is occlusion. You see that this object is actually obstructed by other objects. This is hard. And so dealing with that using template matching might require you to actually create a lot of little templates here from this object, and then apply each one of those and make sure that in your final output there are enough templates of this object that appear in a certain geometric configuration. And if they do, then you declare that you have found the object. A very computationally intensive process and doesn't scale very well. But instead, what we would like to do is somehow extract directly from this image that's given to you some very descriptive, unique features. So if you can find these features, and if you can find the same features in this image, then we can match them and we can recognize the object.
So this is the key idea. We want to find some interesting points or features, some representative, unique feature points from this object. And these interesting features, they could be found on the same object, on this object, regardless of the differences in their scale and orientation.
Object. And that's exactly what the SIFT detector does. So SIFT is short for Scale Invariant Feature Transform. And we'll describe the theory behind the SIFT detector and its implementation, and also show how it's used to solve some interesting vision problems, simple vision problems such as image alignment and stitching, as well as 2D object recognition. So we're going to start with asking the question, what is an interest point? By the way, this is an area of research in computer vision that has a long history. I think the term interest point really came from Hans Moravec back in the late 1970s. He was looking at what are interesting points in the context of robot vision. And since then, there's been a lot of work in this area that goes to say that edges and corners are not really interesting enough points for a lot of applications. We need things that are a little bit more descriptive. And what has been realized over time is that some notion of a blob, which has some local appearance within it, is potentially a very good interest point to try and find and to use for matching as well. So we'll talk about detecting blobs. By the way, I should mention once again that the term blob is being used very loosely here. It's a patch with a local appearance. And we'll use derivatives of images to actually detect blobs, very much like what we did with edge detection. We'll create a theory for blob detection. And what's nice about this theory is that it can detect blobs over multiple scales. It can handle not only the position of the blob, but also the magnification of the blob, because an object can appear at many different magnifications depending on its depth from the camera. So you have to be able to deal with scale. And so this blob detection theory handles scale in a very elegant manner. And using this theory, we are going to develop the SIFT detector, which was proposed by David Lowe. It's a very clever, very clean implementation of blob detection, and we'll see how it's done, and we'll also show that it is very robust and reliable in terms of extracting interest points from images. Now, that brings us to the point where we can actually detect these points in any image that's given to us. But in order to match a point in one image to a point in another image, in other words, an interest point in one image to an interest point in another image, you really need some kind of a signature that describes the local appearance around the point. So that brings us to the SIFT descriptor. We'll see how we can extract such a description or signature from each one of these blobs, and how to make that signature independent of rotation, scale, and insensitive to things like lighting.
Okay.
Scale.
So what is an interest point? Edges and corners. So corners are more interesting than edges. Edges just not that interesting. Edges, because you cannot identify the location or the length of an edge. Well, let's just spend a few more minutes to identify what is an interest point. Some patches are just not that interesting. For example, edges. Edges, you cannot localize an edge, this edge. If you are asked to pick a point in the image and find it again in the next image, which point would you choose? Okay, if you pick this point, can you be able to identify it in the image? No, so maybe we should pick this corner, and we will be easily identify it again in the image, right? So corners could be an interesting point. So corners is a kind of feature that are interesting, but corners itself are not that interesting. Then not as interesting as, you know, from the video. They call blobs. Blobs. It's just a it's a loose term here. We call this blobs. So the SIFT detector is designed to identify blobs. So this is blobs. So it's a loose term. It doesn't mean it has to have this ball shape. It just means a patch that have some variation in the appearance or colors. Okay, so the interest point here refer to blob-like features. Blob-like features which has a center and a size and orientation. Okay, so back to our previous example, you can see the features identified by the SIFT detector. They are represented by different square. The size of the square represent the blob size, the size of the blob features. Okay, so the interest point here are the blobs. So in next week, we're gonna introduce how to identify a corner using image gradient, and finally, blob detection with LOG and the SIFT algorithm. The SIFT detector is for blob detection. Okay, so hopefully next week we can cover this chapter, cover the SIFT detector. This is the detector. You can see the identify the interesting features, and finally describe each feature using low dimensional feature vector. Okay. All right. Now let's take a 5 minutes break, and the TA will walk you through the lab 1 assignment. Okay. So Xiangyu is our TA. Xiangyu will be responsible for grading your lab 1 and lab 2 assignment.
Hello everyone. My name is Zhang Xiangyu, and I'm very glad to be the teacher assistant in this class. And I'm responsible for the lab 1 and the lab 2. If you have any questions, you can just contact me by email or just in the Teams, you can ask me some questions. And in the lab tutorials materials, you can find our email and just send messages to us. Okay, before I introduce the lab 1, let's see some preparations for the lab assignments. Overall, you should need to be familiar with Python, and the second step is you need to build your own Python environment. This course presumes you all have learned Python before. If not, you can just refer to the official Python tutorials or some video tutorial in the YouTube and other channels you want to learn. Okay, let's jump to the step, and we can see the second step, how to set up your own Python environment. Because in this course, you need the Python 3 and several Python packages such as NumPy, Pillow, and Pytorch. If you know well about how to set up and manage Python environment, you may have installed Python and these packages in your preferred way and ignore this section. If not, we recommend you to install Anaconda and using some IDE such as Pytorch or Visual Studio Code. Okay, first let's see how to install Anaconda. You can just go to the official website and download this and follow the installation packages to finish this step. And the one thing you need to take care is the file step. You need to select just me, and then in the 8th step, you need to add an Anaconda to your Python environment variables. Okay, if you select these steps, you can jump the second step, and because it will update your environment variables automatically. And after you have installed Anaconda, you can install some IDE. This tutorial told you how to install Pytorch, and I will told you how to install the Visual Studio Code. Because Visual Studio Code is more lighter than Pytorch, you can just download this from the official website, and then you need to add the Python environment to the interpreters. Take this Visual Studio Code as an example. You can select this, select another channel, and in this place, you can select your own Python environment. If you have downloaded the Anaconda, you can just select the base environment. And after this, you can just run your code such as this. It's very easy. And if you have any questions, you can contact any of our teacher assignment assistant. Okay, let's say let's say the lab 1, filter basics and edge detection. Before we introduce the filter, let us see the image and the n-dimension array. Because color images in digital computer are represented as 3-dimensional arrays, It consists of height, width, and channels. Each element of the array is an 8-bit integer with a range from 0 to 255. The shape of this example is the shape of the array. From the example, we can see if the number is small, the color is darker, and the number is big, and the color is lighter. Okay. How to process the n-dimensional arrays? We should use the NumPy. NumPy is a common library for performing mathematical operations on ND arrays in Python. Images can be represented as the NumPy's ND array objects, and you should need to use the pillow packages, pillow point image, to read images, and using the NumPy and the array objects to operate the images. This is an example from the code. Such as this. We should use the pillow packages to open an image, and then we can use the NumPy to process the array, and then we use the pillow packages to save the images. Okay, this is an example. First, we use the pillow packages to read the lingua images, and then we process the arrays with divisions the images to half. So the images will be darker than the original images. Then we need then we can see some manipulate in the arrays. NumPy offers a wide range of operations for processing arrays, including the arithmetic operation, indexing, slashing, and so on. To get a rapid understanding of NumPy, you can just refer to the official tutorial, or you can just ask GPT-4 or some AI to help you. Such as in the Visual Studio Code, you can ask the this Copilot. For example, when you want to write your code, you can like this generate, and told this your requirement. Then it can generate the code for you, and you can just run this. Okay, accept. Okay, such as this. The Copilot writes code is similar with the code writing by yourself. It's very convenient. Okay, let's see some arrays attributes. After you have created your own array, each ND array object has 3 attributes: the arrays type, shape, and n-dimension. Okay, this is not very important, but you should be clear that when you transfer the array to the pillows images type, the ND arrays type should be 8-point byte. Okay. But this point I have but all this process code we have provided you in the code. as filters, we have provided you all the codes. You can just using this. Okay. And after you have learned some arrays attributes, you can create your own array. This is an example to create all one matrix of shape 2 and 3, just using the NumPy once. Okay. After this, you can go to a 6 ones array. And the default data type is float, is the double float. Also, you can just create all the row metrics and so on. Okay, let's jump to these operations. And the array is also very similar to the list. You can do some arithmetic operations such as the addition, subtraction, multiplication, and divisions, and so on. You can try this by yourself. Also, it can perform some various mathematical operations like sine, cosine, and so on. Because ND arrays is an n-dimensional array, so you can modify the array shape via the reshape function. Take this example. The array is a list, and when you use the reshape, it will be a 3 multiply 3 array. And you can using the indexing, slashing, and a lot of operations. These operations you can try by yourself. Okay. Let's say the filter basics. First, I will introduce the convolutional filters. Convolution can be performed using the ND-images convol function. Operations like Gaussian smoothing and Seubert filtering often involve convolution. Here is an example of how to use it. From these packages, you can just import the ND image, and the ND image have the convol functions. Giving the gray is yes. Okay, we can see an example of this. All of this is the ND arrays operations. You can try by yourself, and we focus on the filter basics. Okay, first, we need to transfer the images to the gray images, and then we can do some following operations, and we can like this. The gray is our input images, and the width is the input kernel of filters. Just using the ND images function, the convol function, it includes the input image and the input kernel, and we can find the output image. By using this kernel, it will understanding the details. Also, let's see the Gaussian kernel. We can define the Gaussian kernel manually. This is a classical Gaussian filter, and also we can use the convol function to to process the input gray images by using the Gaussian filter, we can see the results. Okay, you can see the image is more blurred than the original images. There's some examples. Yeah. You can try this code by yourself, and you can get the results such as this. So the next step is how to sharpen your own images. Because convolution can be utilized to sharpen images, which involves enhancing the image's details. The first step is to get the image's details. We can using this formula. The details means that the original images to using the blurred and the original images, we can get the detailed images such as this. Okay, we can see the example. And then if you want to add got the sharpened images, you can just using the original images to add the detailed images. Like this. Okay. I will show you the old images. This is the original images processed by the Gaussian filter. You can see that the images is blurred. So you just following the formulas, you can get the sharpened images like this. You can see that the detailed information will be sharpened. Okay. How to achieve this step by step is your homework, and in this class I only show you the results. You can just follow in this formula to achieve your own code. Also, there is something you need to be take care, because the results sharpened images obtained from the equation 2 may have values exceeding the range of 255. You need to track them within the valid range of 0 to 255. Otherwise, it will have some bugs in your code. And the second filter is named the median filter. Median filter is effective in removing salt and pepper noise. What is the salt and pepper noise? A typical example is the runs. For example, we can see that. Oh, sorry. Dish. You can see there are some runs in the images, and using the Gaussian filter, it don't have some effect. But when you use the median filter, it can remove the runs from the images effectively. Let's say let's say what is the median filter? When working with the color images, it is necessary to apply the median filter to each channel individually. The input is 3 multiply 3 neighborhood, and we will replace the center points. Original center points is 6, and we replace the median number. The median number is 38. We use the 38 to we replace 66 to 38. Okay. By using this operation, we can remove the salt and pepper noise effectively. Okay, I will show you some results. We also take the rain images as example. After we use the medium filter to process the images, we can see the results. You can see this. In these images, there are no rains, so you can just use the medium filter to denoise, especially for the salt and pepper noise. Oh, okay. This is also an example of the results. You need to achieve your own code by yourself. This is also another your homework. Then we can see the edge detection via Canny Edge Detector. As you have learned, the Canny Edge Detector contains the following steps. The first step is the Gaussian smoothing. And the second step is the Subel operator. Then we can using the non-maximum separation to process the Subel operator's images, and finally we use the thresholding to get the final results. For the sake of simplicity, let's focus on the grayscale images. Because the 3 channels need a lot of operations. We translate the RGB to grayscale is just for the simplicity. First, you need to convert color images to the grayscale. This is the formula to converting RGB to grayscale, and in the basic code, we also give you the functions. You can just using the functions. The functions is in the edge. Sorry. In this place. Yes, in this function RGB to gray, you can just use these functions, and you don't need to achieve by yourself. Before the Subel operator, you need to operate the Gaussian smoothing, and then I will just introduce the Subel operator. As I have introduced before, the Subel operator is also the convolution filters. Giving an image A of shape, height, and width, the Subel operator computes the magnitude of the gradient of A as follows: the Gx and the Gy, and then you can just got the final result J by using the square roots. The NumPy packages give you the functions you can just use. Okay, let's say some example. We take these images as an example. This is road images. First, you need to translate the road images, the color images to grayscale, and then you need to operate the Subel operation, and finally you can get this result. That's to me. You can find that you can get approximately the edges of the root images, but there are also some see this, but there are a lot of noises. Then you need to using the non-maximum separation to denoise the results. the locations of the output from the Sorbet operator is not very precise. It turns to generate response in multiple adjacent pixels, make it challenging to determine the exact location of edges. In order to address this, we using the non-maximum separation operations. As you have learned from this class, to compare its gradient with its neighbors along with the perpendicular direction of edges, which is the same as the gradient direction, we begin by calculating the angle between the gradient using this formula, using this equation. Okay, take this is as an example. The red line is the edge, and the black line is the gradient. So we then need to determine, okay, let's say this. We need to determine the two neighboring elements N1 and N2 that need to be compared based on the value of theta. The theta is the gradient. You can compute the theta by using the arctangent formula. Okay. The red line is the edge line, and the black line is the gradient. After we got the theta, we can using these equations to determine which N1 and N2 we should choose. Take this example. The theta is between 67.5 and 112.5. You just need to use these equations, and you can find the N1 and N2 you need to choose. From these equations, that means the N1 and N2 is this point and this point. Okay. After you have found the N1 and N2, finally, you can use this formula to using this formula to determine any point less than N1 or N2, we will set this to be 0. And if the Jij bigger than N1 and N2, we will keep this. Okay. The key step of the non-maximum separation is how to get the theta. We use this formula to get the theta, and then we need to following the using the following formula to determine which N1 and N2 we need to use, and set all points less than N1 or N2 to be 0. And finally, we use the double threshold to determine which threshold we need to keep, and the others we need to set to be 0. Once non-maximum separation is completed, the next step is to binarize the gradient magnitude. In the standard Canning edge director, this involves applying two-level thresholding and conducting connectivity analysis. Since the gradient magnitude ranges from 0 to 361, A suitable threshold can be chosen from a range of these. For example, we can choose the low threshold as about 200, and any point lower than this than 200, we can set this to be 0. Okay, let's just see some examples. Yes, this is the images we have. We have processed by the Sobel operator. We can see that there are some noises, but after we have using the non-maximal separation, we can see that the noises is less. And then we need to using the thresholding method to get the final results. And this is the final result. Okay, we are using the thresholding method. We highlight all the edges. And these 3 pictures is the comparison of the 3 steps, but it's not very clear. Okay, this is the details of how to achieve the thresholding. You can following this. You need to achieve these steps by yourself, and I only show you the results. This is also another example. After using the thresholding, some not very important edges will be. We will give up some not very obviously edges. And the final part is named the half transform. It is a bonus part. The before part, this part is after you have achieved this part, you will got some bonus scores. Okay, let's see this part. It may be difficult. Once we have obtained the edge image, the next step is to identify geometric shapes such as straight lines, circles, and so on from the edge maps. A commonly used method for this purpose is the half transform. In this section, we will illustrate how to detect straight lines using the half transform. A line on an edge image is represented by the equation like this. Each line on the edge images correspond to a point in the half space, with the line being defined by its slope and its intercept. That means every line, every point in the current coordinate is a line in the half space. But using this method, we can it has some limitations because this algorithm fails to detect the vertical lines because the slope A becomes undefined or infinite. To address this issue, we can use using the cosine and sine method to represent the normal line. After using this method, also every point in the declared coordinates become a sine line in the half space. You can see like this example. X1, Y1 is the below line, and the X2, Y2 is the up line, or we can see the cosine line. Okay. After you have transferred the images into the Herf space, you can got this route. Now we can devise a voting procedure to determine the most like straight lines following these steps. The first step is to translate the images into the Herf space, just like this. And then we can find the points. The points with a lot of curves straight this point. That means this is a straight line in the images. So by using this method, we first translate the images into the Herf space, and then we only need to find the points that a lot of lines to have for that means for each edge pixels iterate through all possible values of theta. We only need to calculate the points through a lot of lines, and then we can find the straight lines in the original images, and then we can find the local maximum identified by the top n cell. Top n cell means the top n point which through a lot of curves, and we can find the straight lines in the original images. Okay, let's say some examples because it is more obviously. Okay, we need to this is the results of translate the original edge images to a Herf space, and we can see that there are several points have through a lot of curves, and this point means the straight lines in the edge maps, and we can find that, and we can using the red color lines to represent the point in the Herf space, and we can got the final result. We can see that all the lines is the straight lines in the edge maps. Okay, this is how to achieve the Herf space, using the Herf space to detect the straight lines. And finally, I will introduce the detailed assignment you need to finish by yourself. The part 1 and the part 2 is the basics assignment you need to finish. The part 1 have 4 points, and the part 2 have 6 points. And the bonus part only have 2 points. Although it have a little points, but it is the most difficult. But after you have finished the bonus part, you will got addition to score 2 points in your final results. Okay, just following the requirements to finish this part, and then I will introduce some summarization instructions. The OpenCV packages CV2 is not allowed in this assignment. You need to achieve the convolution operations and the Subel operator operations by yourself. And your submission should contains all intermediate results, such as you can just submission Jupyter notebooks results just like this. Just like this, you can save every intermediate results like this, or you can save the results to a folder named date folder. Also, you have also the assignments require some discussions, such as in the part 1, step 3, and the part 2, step 1 and 4. You need to save the discussions and write them in the discussion PDF file. Also, finally, you need to provide your executable programs, the Python file, and so that we can reproduce your results. And you need to submit the results before November's. You have 1 month to finish this, to finish your homework. After, you may submit as many times as you want, but only the last submissions before the deadline will be graded. If you exceed the deadline, you will your score will you may not got all the scores. Okay.
Okay, so just some clarification. So the highest mark you can get for lab 1 is 12 points, which correspond to 6 points in your overall assessment, overall grade. Okay, so the highest mark you can get is 6 in your overall grade. Okay, and if you have questions, you can reach out to Xiangyu on Microsoft Teams. Just send him messages. All right. Okay. If you have questions, you can approach him now, or send him messages. Okay. Okay. See you next week.